Hello everyone, and welcome to the 83rd episode in our AI and You podcast series. Today is Friday, January 28th, 2022, and I'm your host, Vikhar Saidi. I'm a computer scientist and engineer, a lecturer, and a consultant. I'm also the author of several books. My most recent book is about artificial intelligence and is titled The Genome Affair. The Genome Affair is a speculative work. It examines what the world might be like if some of the more extraordinary capabilities forecast to be realized in AI over the next 20 to 30 years were actually realized today. Given the growing list of frightening existential threats humankind now faces, the book pays particular attention to the impact AI is expected to have on world affairs. The book is available in ebook format for those who prefer to read on a digital device, but it's also available in a high-quality paperback edition. The Genome Affair is available on Amazon, so I hope you'll take the time to read it and to leave a review. Amazon book reviews are very helpful for writers. I'm very interested in how science and technology influence world affairs and the big questions facing humankind, studying at the confluence of the great disciplines of human history, political science and thought, international affairs, science and technology, offers a deep understanding and pedagogically important lessons of how advances in human endeavor have influenced and impacted civilization. I'm available to give talks on artificial intelligence and its related technologies, and on the impact AI is expected to have, or is already having, on our world. If you'd like to get in touch with me to arrange a web-based event or consulting meeting with your company or organization, you can find my contact info in the podcast notes below. Please make sure to subscribe to my channel, like this video, and share it with others if you find the content valuable. Thank you. And now, on to today's podcast. In our last podcast, episode 82, I spoke about artificial intelligence in 2022. Where are we now, and what does the future hold? In today's podcast, episode 83, I'll speak about whether protein folding is our most important achievement in AI so far. This is the second of the podcasts in this series. Let's get started. Over the past 5 years, rapid advances in artificial intelligence have been applied to solve many interesting real-world problems, from applications in education and health, to radiology and social media, to natural language processing and speech synthesis, to lethal autonomous weapon systems, weather prediction, and robotic surgery, and so much more. AI is accelerating progress across countless disciplines to a very impressive degree. But there is a consensus coalescing within the AI thought leader community that recent advances in the application of AI in the complex and esoteric field of structural biology, specifically in the area of protein folding, may be AI's greatest achievement to date. Protein folding refers to the three-dimensional shape assumed by a protein before it begins life as a nanomachine in the human body. We'll come back to this in just a minute. DeepMind, a London firm acquired by Google in 2014, is perhaps the world's preeminent AI company. On November 30th, 2020, the firm published an article in the journal Nature, confirming that they'd solved the previously insurmountable 50-year-old protein folding problem using a proprietary deep learning AI agent known as AlphaFold. It was a shocking development that upended the world of structural biology. The implications of the publication were unprecedented, and they continue to reverberate across many disciplines today. For the past 50 years, scientists have endlessly toiled over the protein folding problem in a never-ending struggle to understand the three-dimensional structure of protein nanomachines. It has been the grand challenge in biology. In order to understand the final structure of proteins, scientists needed to make the protein production factory, the ribosome, express a sufficient quantity of a particular protein, and then harness them before cajoling them to crystallize. This proved to be extremely challenging. If they succeeded in crystallizing a sufficient volume of these folded proteins, they could then use X-ray crystallography to better see and understand the folded structure. But it was common for this process to take years, and sometimes even longer. In fact, many scientists have spent their entire careers and lives attempting to find the folding structure of various proteins. It would be far better if we could simply predict the three-dimensional protein folding structure by simply examining the string of amino acids involved. At this point, most readers will undoubtedly be wondering why the three-dimensional shapes of these proteins are so important. Before we answer this question, let's spend a minute to shape our understanding of what proteins are, how they are made, and what they do inside our bodies. Ribosomes are factories within our cells where 20 distinct amino acids are produced. Strings of these amino acids are linked together in unique ways to form proteins, and then, within a few milliseconds, physics intervenes to direct the final three-dimensional shape of the newly formed protein. There are 20,000 distinct proteins in our bodies, and each one folds into a distinct shape, and thus has a different function. Thus far in nature, we have identified approximately 100 million proteins. These proteins can fold into 10 to the power 300 distinct three-dimensional structures. For reference, there are 10 to the power 80 atoms in the known universe. And so, for all intents and purposes, this represents an infinite number of potential folded structures. Once folded, these proteins perform mechanical and chemical functions within cells throughout our bodies. Common proteins include hemoglobin, which transports oxygen within red blood cells, and insulin, which metabolizes glucose. In pharmacology, the three-dimensional folding pattern of a protein is crucial information. Once pharmaceutical scientists understand the folding pattern of a protein, they can design a chemical compound that can optimally bind itself to the protein in question in a very specific manner. This process, in effect, alters the protein's function or disables it, thus preventing or intervening in potential pathology. So, we can see that rapidly understanding the pattern of protein folding is crucial in developing new prophylaxes and therapies. This is a revolutionary advancement that is expected to dramatically reduce the time required for the development of new drugs. AlphaFold's ability to accurately and rapidly predict protein folding structures is now improving our understanding of how to break down the plastics polluting our oceans as well. These plastics are currently being deposited in our oceans at the rate of 10 million metric tons per year, and with time they break into ever smaller parts due to sun and water erosion. They eventually turn into microplastics that are then ingested by marine life. Through this process, microplastics enter the food chain, and so they are eventually consumed by humans. This, of course, can have impacts on human health that are not yet understood. AlphaFold's ability to understand the three-dimensional shape of enzymes that are effective in breaking down plastics into their base chemical components promises to have a great impact before these plastics can do further damage to marine ecosystems and eventually human life. Until next time then, this has been the AI and You podcast with author Vicar Saidi.